Kia ora and hello. My name's Professor Julian Paton. I'm from the University of Auckland. I'm Director of Manaaki Manawa, the Centre for Heart Research, and also co-direct Putahi Manawa, which is a centre of research excellence which endeavours to improve heart health equity across Aotearoa, New Zealand. I've been interested in hearts and heart disease for many, many years. The heart's an amazing organ. It beats at around 2.2 billion times during life. It's a muscle that never fatigues, and it also generates its own electricity. The heart, unfortunately, suffers from a number of conditions. Rheumatic heart disease is a disease that's associated with a developing country rather than a developed country. Children in New Zealand, unfortunately, have high levels of rheumatic heart disease. Our Māori are 26 times more likely to have rheumatic heart disease than non-Māori, non-Pacific children. And our Pacific children are 80 times more likely to have rheumatic heart disease than non-Māori, non-Pacific children. Just to remind you, rheumatic heart disease starts as repetitive sore throat infections, streptococcal infections, that then trigger an autoimmune response. That autoimmune response generates antibodies in the bloodstream that attack the heart valves. And there's something unique in the heart valves that express what we call an antigen onto which those antibodies attach to destroy the heart valves. And you can see in this slide the problems this causes. First of all, there is a problem with the valves becoming thick and stiff, which means that they don't close properly, and they certainly don't open to the extent that they should. We're going to look at this in a little bit more detail. Here we have an image of a heart, and I'd like you to focus on the valve that separates the upper and lower chambers on the red side. This is the left side of the heart. You can see that the valve is opening and closing with each heartbeat, and it is allowing blood to move in a unidirectional way from the top chamber, the atrium, into the lower chamber, the ventricle. Now, one of the heart sounds that we hear is indeed caused by the movement of the heart valve, and that is a lub-dub sound, and you hear that through a stethoscope. Unfortunately, the situation in rheumatic heart disease is that the valves become thickened and stiff, and therefore they don't open or close. If they don't close, then they don't function as a valve should, which is to prevent backflow of blood. Here you see the heart beating, and you see the movement of blood that's coming from the top chamber into the bottom chamber, but as the bottom chamber contracts, a lot of blood is forced up into the upper chamber from where it has come, and this is pathological. This is heard through the stethoscope as a sh noise, regurgitation. Currently, we have ways of addressing heart valve disease, including rheumatic heart disease, by either implanting a valve made from metal, titanium, or a valve that has come from an animal. The titanium valve here on the left has problems associated with the need for lifetime coagulation therapy to prevent blood from clotting, and that has severe side effects. On the right side, the animal valve, they will last somewhere between 6 to 10 years, but can also be rejected by the body because it's foreign to the body. In conditions of rheumatic heart disease in young children, these individuals, once identified, are going to experience a lifelong journey of severe open heart surgeries. These surgeries are extremely traumatic, involving opening the chest and then opening the heart to put the valve in. If these valves only last a certain period of time, as they do currently, or they are rejected by the body, then as you can imagine, those valves would need to be replaced. But the big problem for children is that the valves are fitted to a small heart, and as that child grows into an adult, that heart will grow, but the valve that's been put in it will not. As a result, further operations are going to be needed to put in a valve that is of the same size as their heart. So what's the answer? The answer is that we're going to take a skin biopsy from a patient with rheumatic heart disease, and we're going to grow those cells in vitro in culture. At the same time, we're going to take a three-dimensional image using magnetic resonance imaging of the child's heart valve. This will allow us then to make a three-dimensional print of their valve, but printing using a material that will sustain the growth of cells. It's a kind of growth matrix-like material that we can impregnate with all the nutrients and the growth factors. Once we have the skin cells, we can convert them to stem cells, and we need to do that because it's only from the stem cells that we can then make heart valve cells. So the stem cells will be seeded onto the 3D print of the heart valve that we have made from those MRI images. Once the heart valve is formed and is growing, we will pressure test it, and we will also put it into lambs to make sure that it actually grows as the lamb's heart grows. Once that is done, we will be in a position to do world-first study of putting it into a human patient with rheumatic heart disease. This will be world-leading from the standpoint that only a single operation will be needed, that the valve will not be rejected because the cells of origin of that valve have come from the patient themselves. And we hope that this valve will be robust and last a lifetime. Can we do this? Of course we can do this. First of all, we have a multidisciplinary team at Manaki Manawa at the University of Auckland. And second of all, we have unique facilities that allow us to carry this project all the way from the cell biology, preclinical testing, and indeed the first in human study. That is the wonder of Manaki Manawa.